Welcome to the third lecture of the fourth week of the course of machine learning. This lecture will be about decision tree learning algorithms. For practical reasons, we will break this lecture down into two parts. This is part one. The agenda for this lecture is as follows. We'll first talk about decision trees in general. Then we will focus on a specific kind of algorithms called top-down induction of decision trees algorithms. And then we will talk about some information theoretical measures needed for making crucial decisions in these algorithms. Then we will have this break for part two, and then in part two we will look into the ID3 algorithm, which is, I can say, is a default or prototypical algorithm of this kind. And after that we will talk a little about one of the key problems for this kind of algorithms, which is overfitting, and how to manage that problem through something called pruning. And then finally we say a few words of some alternative algorithms within the same category. The challenge here is to design a decision tree such that the tree optimizes the fit of considered data items and the predictive performance for still unseen data items, which we call the minimal prediction error. Decision trees analyses are of two main types. So on one hand we have classification tree analysis, when the leaves are labeled according to the k-target classes included in the dataset. Regression tree analysis when the leaves are real numbers or intervals. Decision trees represent the disjunction of conjunctions of constraints on the feature values of our instances. But a decision tree can also be seen as an equivalent to a set of if-then rules. If-then rules are also many times used for decision situations. So in this case, each branch represents one if-then rule, where the if part corresponds to the conjunction of feature tests on the nodes from the root to the leaf, and the then part corresponds to the class label or numerical range of that branch. Decision trees and the corresponding learning algorithms have some positive and negative properties. If we look at the positive side first, this kind of formalism is very easy to interpret for humans, and as a consequence also many aspects of the algorithms are easy to grasp and follow. It's a very compact formalism. It's also very natural to handle irrelevant attributes. You will see that when we go into the algorithm, that one of the key things to handle the choice of attributes. Also, there are reasonable ways of handling missing data and other kinds of noise. And these algorithms are also very fast at testing time. Of course, there are some restrictions. So one thing is actually that the only way a decision tree can split the data items is by following the axis of the feature space. So the divisions of the feature space is actually rectangles that follows the dimensions of the feature space. Another thing is that typically these algorithms are greedy in the sense that I always try to find an optimal local decision, which means that and they don't backtrack. They don't. They never go back and change earlier decisions. So this means that because they are greedy, they may not find the globally optimal tree. So for learning this representation, we will now focus on a particular category of learning techniques called top-down induction of decision trees, TDIDT. The scenario for learning here is supervised, non-incremental, data-driven learning from examples. And we have touched all these subjects earlier, so I hope you get the picture. The systems are presented with a set of instances and develops a decision tree from the top down, guided by frequency information in the examples. The trees are constructed beginning with the root of the tree and proceeding down to its leaves. The order in which instances are handled are not supposed to influence the build-up of the tree. The systems typically examine and re-examine all of the instances as many stages during learning. So actually, all the instances have to be stored in this process. Building the tree from the top and downward, the main issue is to choose and order features that discriminate data items in an optimal way. Subtopics that we will touch are the following. Use of information theoretic measures to guide the selection and ordering of features. How to avoid underfitting and overfitting by pruning of the tree. Generation of several decision trees in parallel is another approach. An example of that is called random forest. And finally, we will say something about how you can build in some kind of inductive bias in the algorithms. One property of nodes in a decision tree that is important for the rest of our discussion is the concept of purity or homogeneity. So when we start a build-up of a decision tree, we start with a data set, and we start with the root of a tree. And initially, the entire data set, that all training instances, the entire data set is associated with a root. So this you can see in the picture, the small example to the right. But for every decision split we do in this process of building up the tree, based on a chosen feature and its values, the data set is partitioned, and the subsets of the data sets become associated with the nodes of the split, the new nodes. And this is repeated recursively down to the leaves through the series of decisions we make. So purity or homogeneity refers to the distribution of data items of the K target classes. They are symbolized by colors in the simple example to the right, both for the root and for each of the nodes. Less degree of mix of classes for all the particular nodes implies higher purity for the nodes. So this means that if the elements of a node, the instances associated with the node is of just one class, you have a purity, maximum purity. But if you have an even mix, an even balance of all the classes involved, if you have two classes, you can say you have 50-50. If you have three classes, you're 1/3, 1/3, 1/3. Then you have a minimum purity or maximum impurity. Sometimes people want to talk about homogeneity instead, but in this presentation, I highlight the term purity. So most algorithms in this genre aims at maximizing the purity of all nodes. And of course then we need some means for measuring this impurity, and we will now turn into a few alternative schemes for measuring the purity or impurity. As you understood, we need some information theoretic measures, ways of measuring the decision tree nodes and the associated instances in order to be able to understand which is the optimal choice of features to use for discrimination when building up the tree. So what we will do now look at a few two very related but slightly different schemes for doing so. One is we call information gain based on entropy, and the other scheme we call the Gini approach. There are also other ways of doing this. There's something called variance reduction, but we will not talk further about that. I mean, most of these techniques are more or less equivalent. There may be slight difference when we apply one or the other in various applications. There will also be some differences in computation efficiency. Some may be better, but more computational expensive, and vice versa. But I think for the purpose of this course, the most important thing is to understand that in order to build a decision tree according to this kind of methodology, you need some kind of measure. And we will exemplify with two cases. I will now talk about one of the most frequently used information to take measures in this kind of algorithms, and is often referred to as information gain, an entropy measure. So there are two parts here. So the first part, if we start from the top, is the information gain. So really we want a measure that guides us in choosing the feature with the best discriminative power in each decision point. And as we said earlier, actually the goal is to maximize the purity of nodes, minimize the impurity of nodes. And we want a measure that tells us whether which feature has the greatest discriminative power. So actually, the idea with the information gain is to say, oh, look, if we have a measure of purity on node where we are, let's look at what happens if we take this feature and split it with respect to its value, and then look at the subsets of instances that we attributed to each new node that we branch from the node we are. And let's look at what happens to the entropy if we do this split. Then looking at the entropy, of course, of all the new the subsets of nodes associated with the split values. So this is essentially the idea of information gain. But first of all, of course, we need a measure of purity or impurity. So the measure of purity here is in this approach is called entropy, borrowed from information theory, and actually it's defined as for the binary classification case, where we have two classes or one class, and then we have positive example of that and negative example of that. So the measure of purity here is chosen to be the negation of the probability of a positive example times the binary logarithm of that probability, and plus the probability of having a negative example times the binary logarithm of that probability. So this is the entropy definition. And for n-ary classification, we have many classes. It's just the negation of the sum of all the probabilities for having a specific class times the binary logarithm of each of those classes. Okay, so then the only thing that we need then is to create a formula where we infer the gain to choose a feature at a certain point based on the split of this feature. So you can see on the slide, you can see this formula saying the gain at a certain point, which corresponds to a certain set of instances with respect to a feature, is the entropy of the original point, the original node, minus the sum of all the entropies for the subsets of nodes, given that we split the instances with respect to the feature values of the selected feature, but moderated by the division of the cardinality of each little subset divided by the cardinality of the set as a whole. So this is the definition of information gain based on an entropy purity measure. Actually, the most frequently used measure in the literature of this kind is the information gain measure with entropy, as we described in the last slide. The alternative used by some people are called the Gini impurity measure, and then we have something we call the Gini gain, which and as you can see on the slide, the difference is not so much in how we decide how we define the information gain, because the information gain is we define with the same principle. It doesn't matter what kind of measure we have of the impurity. So the difference here is how we measure the impurity of a certain set of instances. So you can see that more or less the definition of Gini gain instead of the general information gain is the same. The definition, the difference here is the difference of Gini impurity. So Gini impurity is a measure of the likelihood of an incorrect classification of a new instance of a random variable if that new instance were randomly classified according to the distribution of class labels from the dataset. And this becomes then 1 minus the sum of the squares of the probabilities for an instance belonging to a certain class. Many times the Gini method gives more or less the same result as the other. As you can understand, it's a little simpler to compute because you don't have to compute logarithm. But I take it up here because it's often mentioned, and I think the message is it's not so important which you use if you don't have specific knowledge and really go into the details. But I want to mention it because it occurs in the literature, and the important message then, a summary, is to say you need this kind of measure in this kind of approach. And these are the ones I've described here are the two most commonly used. I will now introduce an example so I can exemplify how these measures can work out. So this example, we have 14 instances, training instances, and each instance is expressed in terms of 4 features: outlook, temperature, humidity, and wind. We each have a few feature values, and then we have a binary classification for this task, whether you should perform a certain activity or not. So this is the case we have. let's now look at the example and how we compute the various measures. So then the first thing to do, of course, is to look at the root of a potential tree for this data set. And as you remember, there were 14 data items in the data set. 9 of them were positive, which means that it's a positive outcome, performing something like playing tennis, and 5 negative. So then we can compute the entropy of the root node, and you can see this done here, according to the earlier given formulas. Then we illustrate on this slide how we can try to evaluate the information gain for one specific feature. Let's say the width, which has a strong value and a weak value. So for the weak value, we have to look at which instances would belong to a node branched out based on that feature value. And actually, it turns out to be 8 instances in total, 6 of them positive, 2 of them negative. In the other case, we would have 6 instances, 3 of them positive, 3 of them negatives. Okay, so then when we use the formula, introduced the gain, information gain by splitting by splitting according to the wind feature. That information gain will be the entropy for the whole set that we already calculated, minus the sums of the entropies for these 2 subsets that we described above, moderated by the cardinalities of the 2 sets divided by the original data set. So we end up with a value of 0.4448. If we do the same thing for all the 4 features, you can see down here, for outlook, for wind, for humidity, temperature, the highest value that we get is 0.246, which we get for outlook. And therefore, according to this method, outlook becomes the preferred feature to discriminate the data maze and the first feature that we are going to split from the root. So on this slide, I exemplify exactly the same thing for the Gini impurity measure as for the entropy measure. I will not spend a lot of time on this because it's more or less equivalent to the other case. Actually do the same thing. Instead of calculating the impurity of S, you have to the entropy of S, you have to calculate the Gini impurity of S with another definition. And then, of course, you also have to calculate the Gini impurities instead of the entropies for the subsets of the original set based on the feature values in this case. But then, in the end, when you want to calculate the gain, it's a similar formula that we used earlier. It's just that we used the Gini impurity measure instead of the entropy. And typically we get pretty similar results with these 2 methods. We will now make a short break here and stop this video. So we will continue to discuss learning for decision trees in part 2 of this video. Thanks a lot. Bye.